Welcome to this presentation on the product array puzzle, where we will discuss an efficient solution implemented in C++. In this session, I will be guiding you through this problem solving approach. Let's start with the problem statement. Given an array ARR, our task is to construct a product array res, where each element in res I is the product of all elements in ARR except ARRI. For example, with the input array containing the elements 10, 3, 5, 6, 2, the output should be 180, 600, 360, 300, 900. This problem has certain constraints, such as the size of the array being between 2 and 1 lakh elements, and each element ranging from -100 to +100. Here's an example walkthrough. Given the input array 10, 3, 5, 6, 2, let's calculate the result for each index. For I equals to 0, we exclude ARR0 and multiply the rest 3 times, 5 times, 6 times 2, which gives us 180. Similarly, for each index, we exclude that particular element and calculate the product of the remaining elements. The final result will be 180, 600, 360, 300 and 900. The naive approach to solve this problem would involve iterating through the array for each element and calculating the product of the remaining elements. This gives us a time complexity of big O of n square, which is inefficient for large arrays. Let's look at an optimized solution. The optimized approach involves a two-pass strategy. In the first pass, we calculate the product of all elements to the left of the current index. In the second pass, we calculate the product of all elements to the right of the current index, updating the result array in place. This gives us a time complexity of big O of n, making it much more efficient. The space complexity is big O of n, excluding the input and output arrays. Let's now look at the code. In the first step, we initialize the result array res with ones. Then we iterate through the array from left to right and update the res array to hold the product of all elements to the left of each index. We use a variable called left product to track the running product as we move through the array. In the second step, we iterate through the array from right to left. Using a variable called right product, we update each element of the result array by multiplying it with the product of elements to the right of the current index. Finally, we return the result array, which now contains the product of all elements except the one at each index. Now let's analyze the time and space complexity. The time complexity of this solution is big O of n because we only iterate to the array twice, once for the left products and once for the right products. The space complexity is big O of n as we need an additional array to store the results. This makes the solution efficient and scalable. Let's go over a final example to see how the algorithm works. Given the input array 10, 3, 5, 6, 2, in the first pass we calculate the left products, that is 1, 10, 30, 180 and 1080. In the second pass we calculate the right products and update the result array as 360, 120, 2, 4, 1. The final result is 180, 600, 360, 300 and 900. Now let's look at a few edge cases. For an array with just two elements such as 12, 0, the result will be 0, 12, since multiplying the remaining elements gives the desired result. Another edge case would involve negative numbers like -1, -2, -3, -4, where the output would be 24, 12, 8, and 6. This handles both zeros and negative numbers efficiently. In conclusion, the product array puzzle can be solved efficiently using a two-pass approach with a time complexity of big O of n. This solution works well even for large arrays, providing both time and space efficient solution. By handling edge cases like zeros and negative numbers, the algorithm is robust and reliable. Hello and welcome to this presentation on the neighboring bitwise OR problem. In this presentation, we will explore the concept of binary arrays and the conditions under which an array called original can be derived from a given derived array. The goal of this problem is to determine if a binary array original exists such that for every element in the array, the following conditions hold. For each index I, derived I equals the XOR of original I and original I plus 1 for indices from 0 to n-2. For the last element derived n-1, it must equal the XOR of original n-1 and original 0. The input is a binary array derived containing only zeros and ones, and our task is to return true if such an original array exists and false otherwise. Let's look at an example. Given the derived array 1, 1, 0, the output is true. We can deduce that the original array could be 0, 1, 0. Let's verify. Derive 0 equals 0 XOR 1, which equals 1. Derive 1 equals 1 XOR 0, which is 1. Derive 2 equals 0 XOR 0, which is 0. This satisfies the given conditions and thus the output is true. Here's another example. The derived array is 1, 1. The output is again true. The valid original array here is 0, 1 because derived 0 equals 0 XOR 1, which is 1, and derived 1 equals 1 XOR 0, which is 1. Thus the derived array is valid and the output is true. Now consider the derived array as 1, 0. The output is false, meaning no valid original array exists. Here, no matter how we try to deduce the original array, we can't satisfy the XOR conditions for all indices. So the output is false. Let's go over the key constraints. The length of the derived array is n, and it satisfies the condition n is greater than 1 and less than 10 to the power 5. Additionally, the array contains only binary values, zeros and ones. These constraints allow us to work with efficient algorithms to solve the problem. Now let's dive into the approach for solving this problem. We begin by assuming two possible values for the first element of the original array, original 0. Assume original 0 is equals to 0 and assumes original 0 is 1. For each assumption, we iteratively calculate the rest of the values in the original array using the XOR operation. Then we check if the computed cycle is valid by verifying if the last value matches the assumption for original 0. Here's a step-by-step breakdown of the algorithm. First, we assume original 0 is 0. We iterate through the derived array and compute the next elements of the original array. After the iteration, we check if the last computed value matches original 0. If it does, we have found a valid original array. Here is the code implementation for the first part. We start by assuming that original 0 equals 0, and then we compute the subsequent values in the original array. If the final value matches original 0, we have a valid solution. In the second part of the code, we repeat the process assuming original 0 is 1. Again, we compute the values iteratively and check if the last computed value equals original 0. If it does, we return true, meaning a valid original array exists. Let's now look at the complexity of our solution. The time complexity is big of n because we iterate through the derived array twice, once for each assumption of original 0. The space complexity is constant as we only need a few variables to perform the computation. In conclusion, we have seen that this problem can be solved efficiently in linear time. By checking both possible values for original 0, we ensure that we account for all possible cases. The solution works even for the upper constraints of 10 to the power 5 elements. Thank you for your attention. If you have any questions, feel free to ask.